All right, folks. So now let's get back into this ice melting example again. Something that I think we all hopefully have a nice, happy, feel good situation going on, right? Take a cube of ice out of the freezer, put it on your kitchen counter. It's going to melt spontaneously. No calculations required. But let's actually calculate that to prove that we know how to use these equations. Okay. So suppose 1 mole of ice melts. What is its change in entropy? And here I've got the delta H of melt. Technically we would call that the delta H of fusion if we were being a little bit more precise. And so what we want to do is calculate the entropy change of the system, which is going to be the ice. We want to calculate the entropy change of the surroundings, which is related to the room. And then we want to see if the process is spontaneous overall. And I'm going to put in parentheses, yes, duh. Okay, but let's prove it mathematically. So to calculate that, we're going to rely on these equations right here, that the delta S is delta H divided by T. But now we need to pay attention to which values ooh, bless me. We need to pay attention to which values of system or surrounding we're using. Okay. So if we go and calculate delta S, system. Okay. I've got my delta H, right? And so we know that that's now going to be delta H of the system divided by the temperature of the system. So I've got that number here, 6010. Note here that it's joules per mole. We could have also given that in kilojoules per mole, so that would have been 6.01 kilojoules per mole. And we typically want our entropy calculations to be in just joules, not kilojoules. Okay, so that's been converted for you. So that's 6010 joules per mole. And now what's the temperature of the system? Well, we're going to assume that it's 273 Kelvin. So it has just melted. It's frozen ice. Of course, if we pull this ice cube out of our freezer, I keep my freezer at like negative 30 something Fahrenheit or whatever it is, right? I keep my freezer much lower than 0 degrees. But all the same, let's just assume that our ice is 0 degrees. It's right at its freezing temperature. Okay, 273 K. So now that's a very simple calculation, right? So I can say 6010 divided by 273, and I get 22.0. We'll use two significant digits, 22.0 joule. And because this is like 1 mole of ice, so we know this is joule per mole K. So I'm just going to write the answer as joule per K because we multiply the joule per mole K by, 1 mole, and that would give me like my total amount of heat evolved for that 1 mole. Okay, so I probably should have done that first over here and said times 1 mole. And so we can see that represented on this graph here. Positive, right? We got a positive value, 22.0 joules per Kelvin. So the ice melting has a positive entropy in the system. But we can't say if it's going to be spontaneous when it melts because we need to look at the total entropy. So if the ice is melting in a room that's 22 degrees Celsius, what is the change in entropy of the room? Well, that at first might seem like, how am I going to calculate that? But we remember that we said now the entropy of the surroundings is just the negative delta H of the system divided by the temperature of the surroundings. And this is why we use that like Q reversible, right? Recognizing that I can reverse my heat depending on if I'm talking about surroundings or systems. So now that's just going to be negative 6010 joule per mole times 1 mole, just so I get the total amount for that 1 mole of ice. And then our room was 22 degrees Celsius, which is the same as 295 Kelvin. So we can't use the 273. We've got to use the temperature of the surroundings. And now when I do that, okay, so I get 6010 negative divided by 295. And then now you can see I get a negative 20.4 joule per Kelvin. with 3 significant digits. And so finally, and you can see that represented here. So now finally, is this process spontaneous overall? So if we look at the delta S total, that's going to be the delta S of the system plus the delta S of the surroundings. So that's 22.0 joule per Kelvin minus 20.4 joule per Kelvin. And as you can see, that equals positive 1.6 joule per Kelvin. Because the total is positive, then yes, we have proven mathematically that ice will spontaneously melt when left out on a kitchen counter at 22 degrees Celsius. And you can see that's represented here. So when this plus this, if there's positive, and you can see here the book, they used universe. I find it's perfectly okay to just call this delta S total, because we didn't calculate the entropy of the universe. We just calculated the entropy of like the immediate surroundings on our piece of ice. Okay, so summarizing, if we look at all of the ways that we could combine the changes in entropy of our system and surroundings, and if it's spontaneous or not, then we realize a few things. For one, when the change in entropy of the system is positive and the change of the surroundings is also positive, that will be always spontaneous. Always. Well, if the change of entropy in my system is negative, but the change in entropy of my surroundings is positive, now we have to consider the magnitude of these two things. So in other words, if the absolute value of the change in entropy of the surroundings is greater than the absolute value of the change in the system, change in entropy of the system, if that is greater, then it will be spontaneous. So in other words, even if the system is decreasing its entropy, it's becoming more orderly, which kind of goes against the grain for entropy when you think about it. And we'll talk about more of those examples as we go. But just think about the car, right, that I showed you. That car is not going to spontaneously become more orderly and more clean. It's going to go the other way around, right? It's going to spontaneously go to a state of being rusted out and dirty, right? It's going to want to increase, okay, if it's spontaneous. So if the surroundings have a greater increase than the decrease in entropy of the system, it will be spontaneous. But if the entropy of the system, if it's more negative than the change in entropy of the surroundings is positive, then it will be non-spontaneous. And of course, if we reverse the signs of these, so if now the change in the entropy of the system is positive and the change in entropy of the surroundings is negative, we have to look at which one is bigger to decide if it's spontaneous or non-spontaneous, right? Remember, we want to see delta S total equal greater than 0 for a spontaneous process, okay? So we'll write spon, and non-spontaneous delta S total is less than 0. And so then, of course, finally, if both the change in entropy of system and surroundings are negative, then that's going to be always non-spontaneous. Okay, folks, I'll see you in the next video.